Okay, so counters are components that are going to essentially count, and they are going to count in binary. However, when we think about counting, we think about counting in decimal. So how are you going to count in decimal? If you wanted to keep count of certain activities, say suppose you wanted to keep track of the number of pulses in a particular waveform. So how would you keep track of that? You can design a counter, a 4-bit counter, a 5-bit counter, and so on to keep track of that. So let's take a step back and talk about counting in decimal. How does that look like? Counting in decimal, talking about you know, playing peekaboo, I guess. How do you count in decimal? You would essentially go 0, 1, 2, 3, 4, 5, and you would keep going. And I'm going to conveniently stop at 7 because until that time I so 0 through 7, that is 8 possibilities which I can capture using 3-bit counter. So if I were counting in decimal, I would have 0 through 7 with uh, and I would keep going, in fact. And if I want a binary output, meaning I want a 4 or a 3-bit counter, and I want to take a look at the output of that, how would that look like for the same values? Well, for that, it would look like this. I would have 0, 1, 2, 3, 4, 5, 6, and 7. Now the question is, how did I write all of these? I use the same philosophy, 0, 1, 0, 1, 0, 1 for the least significant or the rightmost position alternates. The second position with respect to that goes at half the speed. So 0, 1, 0, 0, 1, 1, and so on. The next or the most significant output is going to be at half the speed of the previous one. So 4 zeros, 4 ones, and so on. So if I did that conversion, it turns out they map one to one. So how do you think about that conversion? Well, if you want to convert any binary to decimal, you would essentially use what we call positional significance. So, for example, uh, if you had a number 396, well, how do you write that in decimal? You would say 3 times 10 raised to 2 plus 9 times 10 raised to 1 plus 6 times 10 raised to 0. We use 10 because that it is a decimal number system. So we use 10 because it is decimal, and we use 396 because those digits in that particular order are 396, and we are using 0 and 1 and 2 because the position of that digit keeps going from left to right, and when it is all the way to the right, it is indexed 0 and then 1 and 2 and so on. So that's how we write decimal numbers. So if we follow the same strategy for binary, we will be able to convert binary to decimal. So let's see. Let's pick one binary number. Let's say I have 1101. This is a 4-bit binary number, and I want to find out what decimal value this uh, is the same as. So what I would do is I would take this guy and multiply it with 2 raised to 0, 2 raised to 1 here, 2 raised to 2 there, and 2 raised to 3 there. And once I do that, I would add all of them up. So what I have is 1 times 2 raised to 3 plus 1 times 2 raised to 2 plus 1 times 2 raised to 1 plus, sorry, this is 0. And last is 1 times 2 raised to 0. So this gives me 8 and 4 and 1 is 13 in decimal, right? So if I'm counting, uh, the decimal equivalent of 13 would be 1101 in binary, and you indicate binary by writing a subscript of 2 just after the number, and you indicate decimal by writing 10 as a subscript just after the number. So having said that, if I look back, that's exactly what is going on over here, right? So if you convert any binary count like 111 into decimal, you would get 7, and then 011, you would go back, you would look at 3, and so on. So that's how we are writing these two columns. So we count using decimal, so our count goes from 0 to 7 if we were counting 8 numbers. The circuitry that we have is going to count in binary. So it would go from, if it's a 3-bit counter, so 3 outputs are available, it would go from 000 to 111. And like I mentioned in the previous lecture, Q is a letter we used for outputs of circuits. And right now we have 3 different outputs, so we are going to call them, say for example, the least significant, I can call it Q0 for that column, Q1 for that column, and Q2 for that column. That's a 3-bit counter. So that's sort of our motivation, designing a 3-bit or a 4-bit counter. So that's what it is supposed to do. So how are we achieving this? Using the component that we have studied, the JK flip-flop. So if I look at the JK flip-flop that is shown over here, I have 3 JK flip-flops here. I have JK flip-flop 0, JK flip-flop 1, and JK flip-flop 2. So let me indicate the outputs of each flip-flop as, say for example, I will call this Q0, I will call this guy Q1, and I will call this guy Q2. And I've conveniently chosen the indices to be 0, 1, and 2 because I want to use that number to indicate significance. So Q0 is my least significant because the main clock or the count input is connected to that particular flip-flop. And Q1 will change slower compared to Q0 because only when Q0 changes, it will have the ability to trigger the middle flip-flop. So Q1 is more significant than Q0, and then Q2 similarly is more significant than Q1. So it changes slower compared to Q1, and hence the significance. So I have an input called count enable that I have connected to both J and K inputs of all the 3 JK flip-flops. So if I were to set this to a 1, what would happen? If I make count enable 1, then I have a 1 there, 1 there, 1 there, 1 there, 1 there, 1 there. So I can say all the flip-flops are in the toggle state. So they keep toggling whenever they see a negative edge on the clock signal or clock input. If I assume that all these are negative edge triggered JK flip-flops. Let's assume that it is the case for this discussion. So what is going to happen? Can I say that, so if I just look at this region over here, if I just look at that, maybe I can write a statement quickly. I can say Q0 toggles, because we are in the toggle state, Q0 toggles when there is a negative edge, when there is a negative edge on count. Can I say that? Because Q0 is the output of the first flip-flop and the clock input is count. So if I have a negative edge on the count, Q0 will toggle. Why will it toggle? Because count enable, I'm considering that as 1. So we are going to be in the toggle state. Similarly, I can write 2 more statements. So for example, if I copy paste this, my second statement would simply be this. Q0 will become Q1 and Q1 will toggle when there is a negative edge on Q0, because you see this, Q0 is actually connected to the clock input of Q1, the second flip-flop. And in a similar manner, I can write one more statement. Copy and paste. My third statement is going to be Q2 toggles when there is a negative edge on Q1, right? So those three are my three statements. 1, 2, and 3. I hope you agree with those three statements, because by using those three, I can sketch the timing waveforms or the counter outputs for this counter, figure C-1. Okay, so let's do that. I'm going to take advantage of those three statements to perform this analysis. So what I'll do is I'll start with an arbitrary count signal. So let's say I start with 0, 1, 0, 1, and I will keep going that way. And I have Q0. We said the first statement was Q0 toggles when there is a negative edge on the count. So if I assume that all my outputs start at 0, and I can do that by using the clear input. Maybe I cleared the counter at the beginning. So all my Q0, Q1, and Q2 outputs are starting low, 0. And when there is a first negative edge on the count, Q0 is going to toggle soon after that. And it will toggle again over here, and it will toggle again over there soon after that, just after that, and just after that. And similarly, based on my second statement, Q1 toggles when there is a negative edge on Q0. So it will keep going 0 until here, it will toggle there, and that's it soon after that. And then based on this diagram, Q0 is going to be 0 the entire time. There is no negative edge on Q1. Now you see what is happening here. This time it is 0, 0, 0. For the second the next segment, I have this to be a 0, this to be a 0, that became a 1. In the next segment, I have 0, 1, 0. In the next segment, I have 0, 0, 1, and so on. Where have we seen that sequence before? That is our count sequence. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, oh, this is 1, 1. That particular sequence is what we saw over here. Where did we see that? Right there in the 3-bit counter output. So that's how we are going to be designing this counter. There is one problem that you should be aware of with this. Because there is one after the other, this is called an asynchronous counter. All flip-flops in this design, there are 3 of them, they are not in sync with the count signal. So they are not synced with a master clock. The first guy is synced with the count, the second guy responds to the first guy, and the third guy responds to the second guy. So it's like there is a asynchronous nature to this. That is a problem when it comes to counters. And this particular delay problem could lead to what we call transient counts. What does transient count mean? Transient counts. So for example, because there is delay, it may happen that instead of going from, say, over here, it is 1, and over here, the counter value is 2. Instead of going from 1 to 2, it may go from 1 to 3 to 4 to 2. I'm not saying that it does. I'll have to see how it operates to give you the details, but that's what that problem is. Because of the asynchronous nature, it will not jump from 1 to 2. It may go from 1 to a different number to a different number to 2. So if we don't want the two counts that are for very short duration in the middle, those are called transient counts. So that's undesirable. So people design um, synchronous counters instead, which don't have this particular problem. Okay, so that's a discussion on counters and how do we see them and what is the purpose? How do we design them using JK flip-flop? So that's what we have looked at. So I'll take a couple of questions on the chat and then we are ready to look at experiment 7 part C. The So asynchronous counters are time dependent. Well, asynchronous counters and they are all time dependent. So depending on this count signal, whenever there is a count, the negative edge on the count, the counter value is going to essentially increment by one in decimal. However, what I'm saying is because of that one following the other aspect, you could have, instead of going from, you see, you want to go from 0 to 1 to 2 and so on, right, up to 7, and then you want to come back to 0. But one problem that could happen because of this asynchronous counter is, instead of cleanly going from 2 to 3, it might go to 4 and 6 and then go to 3. So that is going to be for a very short duration, but it may happen because of that uh, rippling effect through the various counters. You know, just if I talk about that just a bit more, you see, if you zoom in on this particular aspect, what do you have there? This is one, that is 0 for that short duration, and that was 0. You see, so we actually didn't go from 1 to 2, we actually went from 1 to 4 to 2, right? So those are transient counts. There is a delay. You're talking about the delay in writing and the so which delay are you talking about? The delay in the circuit or delay in your the video in the circuit? Oh yeah, so you see this Q0 changes after, soon after there is a change in the count. So there is a propagation delay through a JK flip-flop, very small, maybe a few nanoseconds, but with respect to, so when the JK flip-flop sees the negative edge on the count, Q0 changes a few nanoseconds after that. And when there is a negative edge on Q0, 20 nanoseconds or a few nanoseconds after that, there is a change in Q1. So if I take a look at it very, very, if I zoom in to that timing diagram a lot, then there will be delay because of the propagation delay through the JK flip-flop itself. So the output cannot change immediately as the input changes. There will be a delay because they are logic gates inside them, inside the JK flip-flops. They are wires, they are logic gates. So it will need some delay through because of the propagation through the gate. All right, questions. So that's sort of a brief discussion on counters, um, some issues with counters and so on. Um, Let us now look at, well, let's stop this and